In this video, we'll discuss the integral test and p-series. So last time we talked about the geometric sums and we talked about the nth term for divergence. And really with that nth term, that's all we could tell. And so here we're going to move on and look at some convergence tests that apply to that applies to series with positive terms. So far we've seen two tests, and they are your geometric series test. And then we said that if that ratio was between, the absolute value was between 0 and 1, then that series converges to the sum, and here we have our formula. We also talked about when that ratio was outside or absolute value greater than or equal to 1, then we talked about the series diverging. And then we also talked about an nth term test for divergence, and we saw that the limit as n approaches infinity of a sub n of some series then is not 0, then that series diverges. So for this first example, they are asking us to determine whether or not this series will converge or diverge. And so we do have to do some rewriting with some of these. So for this one, notice this exponent here. So we're going to rewrite this. We have n is 1 to infinity, and we have 4 raised to the nth power over 5 to the nth times 5 to the first. And then we can isolate these two terms. So now we're going to have n equals 1 to infinity of 4/5 raised to the nth times 1/5. And so we see that our ratio is sitting inside there. And we also see that the absolute value of our ratio is between 0 and 1. So we're ready to do, really we can say that this converges, and we can also find out what it does converge to. So we can find that sum, and it's going to be our first term. So if we plug in 1 here, I'm going to have 4 over 25 over 1 minus our ratio, which is 4/5. And so here we have 4 over 25 over, and then we're going to have 1/5 here. And so we see that we end up here, we're going to cancel, and we have 4/5. So not only can we say that it converges, we can also tell what it converges to. All right, so for our next problem, very similar here. We do need to do our nth term test, and I didn't on the other one. I just saw that it was geometric. We can look at the limit as n approaches infinity of our 5n squared plus 3 over 2n squared, and we see that does equal 5/2, which is not 0. So here we can say that this diverges. So after we've looked at a few terms of a sequence of partial sums, it helped us tell whether or not we had a geometric or telescoping series. And again, we'll see in many cases where this is not going to help. So that means that we've got to be pretty good at using all the different tests to determine convergence or divergence. And for everything that we're going to do from this point forward, we are going to talk about all the remaining different tests. So we've already gotten the geometric, and we've talked about the nth term. And now we're going to talk about the integral test and a p-series, which is going to include your harmonic series. Okay, on this slide, we're looking at exploring and really developing the integral of a series. And so we'll come back to this if we have time, but we're going to move on to other things. This test here, looking at the idea of using an integral test to tell for whether or not we converge or diverge. And this test is not really used that often. It is a useful test for developing what's known as the p-series, But as far as your integral test, it must satisfy being continuous, positive, and decreasing. And if it satisfies all three of those, then we know that if we look at the integral from 1 to infinity of f of x dx, if that is convergent, then our series is convergent. And if divergent, the series is divergent. All right, so for example 2, we are going to look at the integral test here. And do keep in mind, still again, our first test for all of this would be our nth term test to make sure our limit does go to 0. So we do have the possibility of convergence. And we can do that nth term test in our heads pretty quickly. And we see that the limit here would approach 0 as n grows without bound. So the next thing, to make sure this does satisfy all of the different parts of the integral test, then we have to make sure that this is positive, that it is continuous, and we are decreasing. And so that is something I think we can see pretty quickly, that this denominator is going to stay positive no matter our values, and we can chunk in a few values if need be. Notice we would get 1/2 plus, and then our next term is going to be let's see, 2 squared 1/5, my brain's not working, plus 1 over 3 squared plus 1, and so forth. So we see that our terms are positive, and we are, notice each term is decreasing there. So we have satisfied that. And so now we're going to set up our integral test. And so we're really looking at our integral from 1 to infinity of 1 over x squared dx, or x squared plus 1 dx. And so this is our infinite here, that infinite integral. It's improper, so to speak. So we're going to do something that's similar to a u substitution here. And I'm going to talk about this being the limit. And we're going to pick a nice variable. I'm going to pick b approaches infinity. And I'm going to replace that infinity up there with 1 to b of 1 over x squared plus 1 dx. If we integrate 1 over x squared plus 1, then that's going to be our inverse tangent. So this really turns into the limit as b approaches infinity of the integral. Well, we can go ahead and do our integral. So that's going to be inverse tangent. That's one of our formulas of x evaluated from 1 to b. And so that's going to turn into our limit as b approaches infinity of the inverse tangent of b minus inverse tangent of 1. And so here we're going to plug in, and what this is going to say for us right here, whenever we substitute that in, that's saying tangent of what angle is going to be tending toward infinity. And so that's going to be where we have an asymptote. And that asymptote here is going to be at pi over 2. So that first term is going to be pi over 2 minus, and then for our 1, inverse tangent of 1, that same tangent of what angle gives me 1, and that's going to be pi over 4. So the difference here is going to be pi over 4. Now, an important note for us, that just tells us, since we got a nice finite number here, that tells me that this series is convergent. It does not tell me what the series converges to. Pi over 4 may not be what the series is converging to. We just know this particular series is convergent. Okay, let's look at part B. And again, we can extend out some terms here. if we need to, or we can just look at it in our minds here, what's going on with it. We do need to do our nth term test, and we see very quickly that this limit would be 0. And so looking at some of the terms, if we plug in, we're going to have a half plus 2 over 5 plus 3 over 10 and so forth. So notice that we are positive. It does look like we are decreasing, and this is continuous. So let's go ahead and apply our integral test here. So we're going to integrate from 1 to infinity, and I'm just going to change these over to x's. So x over x squared plus 1 dx. And so from here, we can go ahead and do that, I guess like a u substitution is what we can look at it as. And we're going to integrate from 1 to b of x over x squared plus 1 dx. And here, the derivative of the bottom is almost the top. We've got an extra 2, so I'm going to balance that by putting a 1/2 out front, and I'm going to put that all the way back out in front here. So I have the limit as b approaches infinity of, and this will be the natural log, and it is absolute value of x squared plus 1, but x squared plus 1 is going to stay positive, so I don't have to worry about those absolute value bars. And we are going to evaluate this from 1 to b, or b to 1. So I have 1/2 times the limit as b approaches infinity of, and if I substitute in, I have the natural log of b squared plus 1 minus the natural log of 2. And here, notice if I substitute in infinity there, that term is going to shoot off toward infinity. So subtracting natural log of 2 for huge values of this is not going to matter. So notice that we headed out toward infinity, so this will be divergent. Okay, so for our next part, we're comparing two series, and we needed to see why 1 over n squared converges, but 1 over n does not. So here we have the different series, and we can go through this grouping of values, and if we do go through, and this was Bernoulli's way of proving this, and if we do evaluate each individual value here, you do get 0.5, and then the next one is going to be 0.58, the next one 0.63, and so by the integral test, notice that here, this is not, we're positive, and we are continuous, because again, we're starting at 1, but notice each one of these values, they're not decreasing. And we could see, we've got those sums, but something that's important for us to see is that if we look at the function f of x, which is 1 over x, and it's going to mimic that 1 over m. And if I look at that derivative, I look at f prime at x, that's going to be the natural log of the absolute value of x. And so notice what happens with our natural log function. Of course, we're going to have our point here at 1, 0. But notice that absolute, or the natural log function, after we hit this mark of 1 to infinity, then this is all positive. So that tells me f prime at x, that is all greater than 0 for 1 to greater than or equal to 0 from 1 to infinity. So that's telling me that f is increasing here. So since f is increasing, then this is not going to fit our integral test, and we're seeing how this will eventually end up diverging. Now for the other, we can look at that one, And look at what's going on here with 1 over n squared. Let's just compare that to the function f of x equals 1 over x squared. And so if we look at f prime at x, that's going to be negative 1 over x, which is going to be decreasing. If we look over on this other side, negative 1 over x, that's going to flip stuff over. So we're going to have everything doing like the negatives over here. So then I see that f prime being negative, if f prime of x is less than 0, then I know that f of x is decreasing. And so here we can see that with each individual term, we are continuous, we are positive, and f is decreasing. And so when we go through, we will get a finite value here. And so we see that this will end up converging to a particular value. So here, why are the harmonic series never converges? Well, we could go through and pull out a bunch of different values here and kind of look at them, or we can simply look and see that that harmonic series, after you hit a certain value, the derivative is always going to be increasing. And so here, however you wish to state it is really not going to matter here, just as long as we notice that 1 over x here will be increasing for x being greater than or equal to 1. For this next part, we will be looking at the p-series test, and this is a great test to learn and keep in mind. Notice that you're told that for p values, and again, look at the setup of this. This is a harmonic series. We can look at that for when p is 1. That's going to generate a harmonic series. But notice that these are p-series where p is a positive constant. So that's important for us to remember, because each one of these tests has its own little niche that has to be satisfied. So for the first one, we see that when p, which again is your exponent through here, when p is greater than 1, then we see that our series can converge just by the p-series. But if it's been between 0 and 1, or if p is 1, which is the harmonic series, then both of these will be diverge. And a good place to remember that, again, p greater than 1, so I know 1 over n squared is going to converge. And then down here, 1 over n will diverge. All right, for these examples, we need to determine whether or not the series will converge or diverge. And so for this, we are looking through to see if we have our exponent that we need. So we're going to play around with getting these in the right form so we can see what the value of p would be. So we have n equals 1 to infinity of 1 over n to the first, and then that's going to be times n to the 1/2. And if you're multiplying, well, that looks like crap. If you're multiplying with like bases, you do add your exponents. So that's going to give me 1 over n to the 3/2. And notice that 3/2 is greater than 1. So therefore, this will converge. All right, so for part B, again, very similar, same idea. We're looking at what is going on with that exponent, and that's really n to the 1/3. And so notice that 1/3 is going to be between 0 and 1. So we would say diverge. And let's just go ahead and say diverge by the p-series. That might be a good idea there. Okay, so looking at our next example, for this one, again, you're going to have 1 over from n equals 1 to infinity, 1 over n to the 1/4. And again, that 1/4 is between 0 and 1. So we know this series will diverge by the p-series. Okay, so with part D, I know this had, it just says for us to determine whether this converges or diverges, and sometimes there's easier ways to do things than what we had already been doing. So let's look at, with this one, I would just flip over that e to the negative n. So I'm going to have from n equals 1 to infinity, and that's really going to be 1 over e to the n. Now I have no idea what the value of n is, but I can plug in. Notice it's going to rotate through, so I'm going to have 1 over e plus, and that's going to be 1 over e squared plus 1 over e cubed. And so this is looking awful geometric here. So notice this is an infinite geometric, and so we can really just go back, and I know this is going to converge if my ratio here is going to be between 0, the absolute value of r is between 0 and 1. And notice each time I'm multiplying by 1 over e. So I can go ahead and actually find this infinite sum. Our first term is 1 over e over 1 minus 1 over e. And so that's going to be 1 over e over e minus 1 over e. And so let's see, that's 1 over e times the reciprocal, and those e's will cancel, so I have 1 over e minus 1. And so that's actually telling me that this series will converge, and we're actually seeing, so this converges because infinite geometric, and notice that we actually know what it converges to. Alright, for this one, I know that the instructions said just to decide convergence or divergence, and y'all were shown to go through the integral test. However, I'm far too lazy for such, and there's a much easier way to do this. And this is going to be called the limit, and we'll learn about it here in a little while, but there's no sense in reinventing the wheel here. So this is called the limit comparison test. And the only hitch for the limit comparison test is that our terms have to be positive. And so if I start listing out terms here, I'm going to have 1 plus, and if I plug in 3, I'm going to have 1 over 8 plus 1 over, and if I plug in 4, I'm going to get 1 over 15. So we see that those terms are positive. And so when I do the limit comparison test, I'm going to compare this to 1 over, wait for it, n squared. And I know 1 over n squared diverges. Alright, so for our limit comparison test, we're going to talk about the limit as n approaches infinity. And it doesn't matter which one of these we're going to put on top. So I'm going to go crazy and put 1 over n squared on top, and then on bottoms 1 over n squared minus 1. And of course we have the limit as n approaches infinity. And we're going to do the keep, change, flip business here. So that's 1 over n squared times n squared minus 1 over 1. And we see that that limit is going to head off towards 1. And as long as this value that we get for our limit, that value is between 0 and infinity, aka positive, then whatever this does, then this will also do. Oh, and I wrote diverge. Sorry, crackhead moment. This will converge. Sorry. So with our limit comparison test, we see that 1 over n squared converges. Our limit comparison got a nice positive finite value. So with this, we're going to say this series converges by limit comparison test. All right, next problem. All right, with this series, this is a kind of a crazy, monstrous problem, but I know I'm going to be integrating this, and to save some work here with it, because as far as comparison tests or some other stuff, the natural log kind of throws in a mess with that. So what I'm going to do is go over to the side, and I'm going to do a U substitution so that I can set this up to be something that we can integrate nice and neatly. I would pick on this portion right here, because if I let U be equal to the natural log of U, then my du is going to be, or my goodness, natural log of n, then du is going to be stuff prime over stuff. So that's going to be 1 over n, that's our stuff prime, over stuff, which is going to be natural log of n. And so that will simplify down to be 1 over n times the natural log of n, which is going to be this portion here. So notice that we are able to set up a U sub, and so we're going to look at our integral from 3, because that's where we're starting, to infinity, and this all really boils down to be just 1 over U du. And so, of course, we need to go through and work on that improper integral. So we're going to say the limit, and I'm just going to call that b, approaches infinity of 3 to b of 1 over U du. We see that's really going to become the limit as b approaches infinity of, and we're going to go natural log crazy here. If I integrate 1 over U, that is natural log, but I'm going to go back and replace U, which was natural log of n. And so notice we've got all of that going on, and so I need one more bracket, and that's going to be evaluated from 3 to b. So now we're ready to put in our endpoints. So we still have our limit as b approaches infinity of, and again, natural log crazy, we're going to have natural log of natural log of the natural log of b. So then I'm going to go back and close all these crazy parentheses here. And let's see, make sure I got, okay. And one more here, minus the natural log of the natural log of the natural log of 3. And notice what's going to happen here. B is approaching infinity. So whether or not I'm subtracting the natural log of the natural log of the natural log of 3 is not going to change the fact that this is going to be growing without bound. That does tend toward infinity, so this will diverge. Okay, now we'll look at your integral test and P-series homework. For the first questions here, they wanted us to expand the series or write an explicit rule to determine the sum of the convergent series. So to find that sum here, this pretty much, well, you have to have a geometric series for this to be able to head towards some sum. And so with that geometric, we had to find our ratio, and that ratio is sitting right there. So the ratio is 2/5. Now we do need a first term, so we're going to plug in 0, and so that's going to generate a 1. So our infinite sum here is our first term over 1 minus our ratio, and so that's going to give us 5/3. For number 2, again, very similar, same idea. We see that our ratio here, that ratio is going to be -1/2. And again, that's going to work because remember it had to be bounded, the absolute value of r had to be bounded between 0 and 1, and -1/2 would fit that. So we do need our first term, and again we're plugging in 0, so that's going to generate a 1. So our infinite sum here is going to be our first term over 1 minus our ratio minus a negative. And so that's going to be 1 over 3/2. So that infinite sum is 2/3. Okay, so this next problem, again, very similar. Now, I do encourage you to take that constant term and just move that out. And here's going to be your ratio. And we can just say 3 times our sum, or we could keep it in. Either one is fine. Our ratio is 2/3. Our first term, if we plug in a 1 and we want to keep 3 where it's at, that's going to be 3 times 2/3, which is 2. So now we can find our sum is going to be our first term over 1 minus our ratio. And so that's going to be 2 over 1/3, and that's going to give us 6. All right, so for number 4, this one, if we go through and try to find our rule, and so there's not going to be a much difference here. This is from an earlier problem, because when we start looking at these terms from one to the next, that's going to be n squared plus 1, and it's really 1 over that. And we saw that this was a convergent series. But with this we said was convergent because when we went through our integral test, we saw that this series was converging because we ended up at pi over 4. But pi over 4 is not necessarily the sum, so we do have to be careful there. All right, and I know this says verify by the integral test, and you're not ever asked to use a specific test. So with this, let's talk about here. We could verify that this is positive, it is continuous, and it is decreasing. But to go through that integral test with this, it seems kind of silly because, again, we can go back to our limit comparison test, and the limit comparison test will give us all that we need to do this. Now, again, the only stipulation was that we have positive values, and this will be positive. And so the limit comparison test is great if I can compare it to 1 over n, which diverges, or 1 over n squared, which converges. So with this, if I compare this, I'm going to compare it to 1 over n. And so I'm going to look at the limit as n approaches infinity. And this time I'm just going to put 3 over 2n plus 5. And that's going to be over 1 over n. And so that nice little nifty keep change flip. So I have the limit as n approaches infinity of 3 over 2n plus 5 times, and let's see, that's 1 over n, so that's going to be n over 1. So again, I have the limit as n approaches infinity of 3n over 2n plus 5. And so notice here we get 3/2. So we see that our limit value is finite and positive. So this will do whatever I compared it to, which is this. So I can say this diverges by the limit comparison test. All right, so let's go ahead and look at our next one. And this one has an awful look of geometric. So let's rewrite this. I know this is going to be the sum from n equals 1 to infinity
of 1 over 4 to the n. And if I start expanding out these terms, we get 1/4 plus 1 over 4 squared plus 1 over 4 cubed, and so forth. So this is geometric. And with the geometric, again, we have our first term is 1/4, and also our ratio, it is 1/4. I'm multiplying by 1/4 each time. So our sum here, our infinite sum, is going to be 1/4 over 1 minus a fourth. So we're going to have 1/4 over 3/4. And so here we're going to get 1/3. So we know not only does this converge, but we also know what it converges to. So this one does converge. Okay, so for this one, we do have to make sure that we are continuous, we are positive, and we are decreasing. And all of those can be verified by just going through a quick plugging in the numbers. So really we need to now jump to that integral test, and that's going to be from 1 to infinity of the natural log of x over x squared dx. And that looks like we're going to need to do an integration by parts. I would let be natural log, and then du is going to be 1 over x, dv 1 over x squared. So then goodness gracious, v, if I integrate that, I'm going to get negative 1 over x. And so here we're going to have the limit, because now we've got to adjust our improper integral. And we're going to use b approaches infinity. And so of the integral, and of course when we integrate that, we're going to get, I'm going to make a big, huge bracket here. We've got sunshine, so uv, so negative natural log of x over x, uv minus the integral of v du, so that's going to be negative 1 over x squared dx. Okay, and so let's see, from here we have the limit as b approaches infinity. We have negative natural log of x over x, and I'm going to move that negative out, so we have plus. But if I integrate x to the negative 2, again, that's going to generate another negative. So really that's going to go back to a negative. So I'm going to move that back out to negative. And that's going to be 1 over x. And now I've got to evaluate that from 1 to b. And looking at this, we're going to have a mess here. Let's see. So if I start plugging in, I'm going to end up with, let's see, negative natural log of b over b minus 1 over b. So of course that 1 over b is going to go out to 0. Let's go ahead and just fill in. That's too much to try to do in our heads. So we're going to have negative natural log of b over b. That's the limit as b approaches infinity, minus 1 over b. And then all of that is going to be minus negative natural log of 1 over 1 minus 1 over 1. So let's see. This is going to be a matter of which is growing faster, which is going to be the denominator. So this is going to go out to 0, minus 0, okay. And then minus this is going to go out to 0, and that's going to be -1. So it looks like all of that ends up to be a +1, and so therefore this will converge. Once again, I'm going to be super lazy, and I'm not going to do the limit comparison or the integral test. I'm going to do a limit comparison test, and I'm really focused on these two terms here, n and n squared. So it looks like I need to compare this to 1 over n, which is divergent. So if our limit ends up being positive and finite, we're in great shape. So we're going to look at the limit as n approaches infinity of n plus 1 over n squared plus 2n plus 2 all over 1 over n. Sweet goodness. So this is going to be the limit as n approaches infinity of n plus 1 over n squared plus 2n plus 2 times n over 1. And so we see that here we're going to end up with an n squared over an n squared as n approaches infinity. So that's balanced. That's going to give us 1, which is positive and finite. So therefore, this series is going to do what this series does. And so this diverges by the limit comparison test. All right, for the next problem, we're going to do the integral test. And again, we are positive. We are continuous because we're starting here at 2. And we are decreasing in value because 1 is getting divided by all this crap. All right, so we're going to jump into the integral test. So I'm going to go ahead and change over and start with the limit side because it's always going to be an improper integral. So I'm going to start from 2 to b of 1 over x times the square root of the natural log of x dx. And that is looking like we're going to have to do probably a u sub. I would let u be natural log of x, so du is going to be 1 over x. And so it looks like everything's accounted for. So we're going to look at the limit as b approaches infinity of the integral from 2 to b of 1 over the square root of u, or u to the 1/2 du. And so keep in mind that's really u to the negative 1/2. So we're really talking about the limit as b approaches infinity of, and if we add 1 here, so we're going to get 2u to the 1/2, and that's going to be evaluated from 2 to b, but we need to go back and plug in so that we really have the limit as b approaches infinity of 2 times the square root of, and u was natural log of x, and we are evaluating that from 2 or from b to 2. So we're going to have the limit as b approaches infinity of 2 times the square root of the natural log of b minus 2 times the square root of the natural log of 2. And so this part here, as b approaches infinity, is going to grow without bound. Whether or not we subtract 2 times the natural square root of natural log, it doesn't matter. So this is going toward infinity, so this will diverge. And once again, just like the previous problem, looking at these, I'm going to do a limit comparison test. And I'm going to compare that to 1 over n. And so if we do our limit as n approaches infinity, infinity of 4n over 3n squared plus 1. That's over 1 over n. So that's going to give us the limit as n approaches infinity of 4n squared over 3n squared plus 1. That limit is 4/3, which is finite and positive. So this is going to do what this does, and therefore this will diverge by the limit comparison test.